Welcome back, folks. Before we continue to the next section of this course, let's talk about some of the characteristics of probabilities and events. For starters, let's define what a complement is. Simply put, a complement of an event is everything the event is not. As the name suggests, the complement helps complete the rest of the sample space. To calculate the probability of the complement of an event, we need to set up a few things. For starters, if we add the probabilities of different events, we get their sum of probabilities. Now, if we add up all the possible outcomes of an event, we should always get 1. Remember that having a probability of 1 is the same as being 100% certain. We are going to explain why this is true with several examples. Okay, imagine you are tossing a coin. When it falls, we are guaranteed to get either heads or tails. Therefore, if we account for the sum of all the probabilities of getting heads or tails, we have completely exhausted all possible outcomes. We have accounted for the entire sample space, so we are 100% certain to get one of the two. Since we are certain one of these will occur, the sum of their probabilities should be 1. So, what would it mean if we have a sum of probabilities greater than 1? Recall that probability of 1 expresses absolute certainty. By definition, we cannot be any surer than being absolutely sure, so a probability of 1.5 does not make intuitive sense. Instances where we can get such a sum of probabilities is when some of the assumed outcomes can occur simultaneously. This means we are double counting some of the actual possible outcomes. We will learn how to deal with such issues when we introduce Bayesian notation less than an hour from now. Now, another peculiar case is if we end up with a sum of probabilities less than 1. Then, we have surely not accounted for one or several possible outcomes. Probability expresses the likelihood of an event occurring, so any probability less than 1 is not guaranteed to occur. Therefore, there must be some part of the sample space we have not yet accounted for. Great. Before we move on, we want to tell you that all events have complements, and we denote them by adding an apostrophe. For example, the complement of the event A is denoted as A apostrophe. It is also worth noting that the complement of a complement is the event itself, so A apostrophe apostrophe would equal A. Now imagine if you were rolling a standard 6-sided die and want to roll an even number. The opposite of that would be not rolling an even number, which is the same as wanting to roll an odd number. Complements are often used when the event we want to occur is satisfied by many outcomes. For example, you want to know the probability of rolling a 1, 2, 4, 5, or 6. That is the same as the probability of not rolling a 3. This concept is extremely useful and will definitely come in handy during the next section. We already said that the sum of the probabilities of all possible outcomes equals 1, so you can probably guess how we calculate complements. The probability of the inverse equals 1 minus the probability of the event itself. To make sure you understand the notion well, we will look at the example we mentioned earlier. The sum of probabilities of getting 1, 2, 4, 5, or 6 is equal to the sum of the separate probabilities. The likelihood of each outcome is equal to 1/6, so the sum of their probabilities adds up to 5/6. Now, another way of describing getting 1, 2, 4, 5, or 6 is not getting a 3. Let us calculate the probability of not getting a 3. This is the complement of getting a 3. So, we know that the 2 should add up to 1. Therefore, the probability of not getting a 3 equals 1 minus the probability of getting a 3. We know that P of 3 equals 1/6, so the probability of not getting 3 is equal to 1 minus 1/6. Therefore, the probability of not getting 3 is 5/6. This shows that the probability of getting 1, 2, 4, 5, or 6 is equal to the probability of not getting a 3. Now that we have explained the basic probability notions, Let us get back to the lottery example we explored in the first lesson. In fact, this will happen throughout a series of lessons, where we'll introduce you to the field of combinatorics. We are going to talk about variations, permutations, and combinations, explaining what each of those terms means, when to use them, and how to compute them. Keep up the good work. See you in the next video, and thanks for watching.